Welcome to the first video of section 3.1, and here we get into really stuff that is more directly related to calculus. Limits, yes, are the basis of calculus, but now we get into what are called derivatives. And there are many different applications to derivatives, different rules as to how to find them and stuff like that, and that's what chapter 3 is all about. Mostly it's about the rules to find them and some of the basic applications, and then chapter 4 deals with applications of them. So here we go with section 3.1. One of the biggest ways to use derivatives, or to understand what derivatives are how much is a rate of change. That's what derivatives can be determined as. And one of the most popular or the most basic rates of change is slope. And so the derivative of a particular function is actually could be considered the slope, as long as we calculate it properly. So that's the whole point of questions 1 and 2. Question number 1 asks us, what is the slope of the curve at the indicated point? So what we're looking for is the slope of that line, the straight line on number 1. And to me, you know, if it is drawn to scale, which we have to assume it is, we're going to try and estimate what is that slope. Well, I know it's negative because it's going downhill, and it's not as steep as -1, so maybe it's -1/2, it might be -2/3. It's really hard to pinpoint exactly, but these would be two good estimates as to how steep is that particular graph. Likewise on number 2 is not very exact either. I do know it's negative, so I at least need to have that, and it isn't near as steep as number 1 even. So, you know, this might be a -1/5, or we might be able to go as steep as -1/4. So one way to use derivatives, and even though, notice we haven't even asked or talked about derivatives here in these first two problems, is by looking at the slope. Now, if we look at slope, many of us learn slope as the change in y over the change in x. Well, when we look at derivatives, what we do is we just change this notation just a little bit, and what we do is we say dy over dx, and we just change the delta to the Greek, or not the Greek, but the English version of the same letter, the d. And so whenever we see dy dx, that means the derivative of y with respect to x. And realize these variables here mean nothing. It's always d. Now there are other ways to say it, or to show the same thing. We might say y dx. We might say y prime. And this is really a nice short version that we seem to like a lot. And that's the one that I'm going to use most of the time, but you need to understand these two notations as well. So let's go to number 3. We have the equation y equals x squared plus 3, and at -4, 19, we are going to find the equation for the tangent to this curve at this point. And rather than doing estimations, what the intent of this problem really was, because that we're going to get back to number 5 and do pretty much the same thing, I'm actually going to jump us a little bit ahead and figure out, okay, how can we find a derivative pretty simply? Okay, the derivative y prime. Whenever we have an expression like this, there are one of the rules, one of the it's called the power rules for derivatives, is if we've got a power of x, what we're going to do is we're going to take this exponent, bring it out in front, and become sort of like a coefficient. Now if there wasn't already a coefficient here, then what we'd have to do is we'd have to take this 2 times whatever was there. Well, with that in mind, this is actually an implied 1. 2 times 1 is 2. Now what happens with this is we still put the x, but we have to subtract 1 from that exponent. So that becomes x to the first power. We're not going to put the first power, we're just going to just leave it like that. And then the same rule applies here. Well, what is the x power here? It's x to the 0 power. And so if we take 0 times 3, we end up with 0. Or the derivative of a constant is always 0. That's the rule that we can follow. Like I said, this is jumping just a little bit ahead, but you're really ready for it. So we have y prime equals 2x. That the derivative of x squared plus 3 is 2x. In other words, the rate of change, or the slope of this line, is 2x. Well, we want to know what is the slope at negative 419. Well, what we do is we take the derivative and we're going to plug in the x value, because that's what we want to figure. And this is not a mathematical notation per se, but this is the way I'm going to show it. Y prime, and I'm going to plug in negative 4 in for x. So that's 2 times negative 4, and so we get negative 8. Now what this tells me is my slope is negative 8. And I know my slope is negative 8, my point is negative 419, so all I have to use is the point slope form to find the equation. So it's going to be y minus 19, because that's the y value of the point, equals negative 8 times x minus negative 4. Or y minus 19 equals negative 8x minus 32 and then putting it into the point slope or slope intercept form, we get y equals negative 8x minus 13. And that is the equation for the tangent to that curve right at that point. So this helps in that we can we can actually draw this graph, x squared plus 3. That wouldn't be too difficult. Then we could actually draw the equation y equals negative 8x minus 13 and get the tangent line. Now number 4 creates a little bit of a problem. For square root of x minus x plus 3 at the point 16, 3. Now anytime we have a function with square roots or x in the denominator, the very first thing we want to do is we want to put it into a more user-friendly version. That means get rid of all the fractions by putting in an appropriate exponent, and get rid of all radicals by putting in an appropriate exponent. So 4 square root of x can be written as 4x to the 1/2 power, because we should remember the square root of x is x to the 1/2 power, minus x plus 3. Now notice I haven't taken the derivative yet. All I have done is I have written this in a more user-friendly version, because now I need to take the derivative. f prime of x would be. Okay, remembering the rules from last time, I'm going to take this exponent and multiply by what's in front. 4 times 1/2 is 2. And then, let's see, x, and then I take this exponent here and subtract 1. 1/2 minus 1 is negative 1/2. Right here, I take the exponent, which is 1, multiply it out here in front, so that'd be negative 1. And then here, when I take the exponent and subtract 1, I'm going to get a 0. X to the 0 power is 1, so that remains just at negative 1. We learned last problem that the derivative of a constant is 0. So the derivative, or the slope of the line of this curve, is always going to be 2x to the negative 1/2 minus 1. Now we want to rewrite this in the final version. This is user-friendly, but the reason we don't like it is because of the negative here. So negative simply means we're going to bring it down below, down in the denominator, and since it's to the 1/2, that's going to be the square root. So we get 2 over the square root of x minus 1. Now, what we need to do next is we need to figure out what is the slope right at this point. So what I'm going to do is I'm going to take f prime of 16. So that's not too difficult. 2 over the square root of 16 minus 1 equals 2 over 4 minus 1, which equals 1/2 minus 1, which equals negative 1/2. So negative 1/2 is the slope of this curve at this point. Now, to answer the question, what is the equation of the tangent here? We just need to do some algebra 1, and this is what we get. Y minus 3, because that's the y value of the point, equals negative 1/2 times x minus 16. And then just doing the algebra, we get this. Y equals negative 1/2 x plus 11.